Okay, so welcome back to a new appointment of our pre-seminar. Today, our speaker is Armand Ley from Université de Strasbourg, and he's going to give us a brief introduction to free probability and optimal transport. So, Armand, you can start.
Yes, thank you to the organizer. Thank you, Andrea, for the nice invitation. As you said, I will speak about free probability and optimal transport in 30 minutes to introduce both quite dense topic. So it's quite a challenging talk for me, especially as I'm not a specialist of free probability theory, but I will try to explain you what I understood about this nice theory. So first I will begin with free probability. So free probability. Oh, is it working? Okay. So free probability was introduced by Voiculescu in the context of studying the Newman algebras, and then was expanded to the study of large random matrices in the 90s. So what's the goal, let's say, loosely speaking, of a free probability? The goal is to provide a framework for non-commutative probability theory. So to begin with a formal definition, we need to introduce the mathematical context in which free probability occurs, which is the context, function analytic context of Newman algebras. So what is a Newman algebra? There is a lot of definitions which are equivalent. I will choose one of those possible definitions. So I will say that a Neumann algebra is a subalgebra of an operator of the algebra of operators on a Hilbert on a complex Hilbert space H. So you also ask additional condition to be a Neumann algebra. You ask that Neumann algebra is a closed undertaking adjoints of operators. So adjoint is well defined on the space BH, if H is an Hilbert space, the space of bounded operators. And you ask also that this subalgebra of BH is closed undertaking limits for the weak topology. So you have a lot of topologies on B of H, the space of bounded operators. And for one of the topology, one of the weakest, you ask that it's closed undertaking these limits. So don't worry if you don't know much, as me, about von Neumann algebra. We won't need it too much in this talk, as I will not go into technical details, but I will be kind of sketchy. You need a von Neumann algebra, and you need another object, which is a tracial state on a von Neumann algebra. So a tracial state is an application phi, which is defined on your von Neumann algebra A, and which is valued in complex numbers. So you ask for phi to be a continuous linear form, continuous for, let's say, the weak topology. You ask that your application phi is positive on positive elements, that is, on elements that can be written A times the adjoint of A. And you ask also that your tracial state is normalized, that is, the phi of the unity is equal to 1. And you ask for the trace property, that is, you ask that for all elements AB in your von Neumann algebra, phi of AB is equal to phi of BA. So this is the formal setting of a study, and now I can define what is a non-commutative probability space. So a non-commutative probability space is a pair A phi, where A is a von Neumann algebra and phi is a tracial state. So what is the link with classical probability? For the moment, it's just a formal definition. So A, you can identify elements of A as random variables, and you will identify your tracial state phi as the expectation operator. So I made a table to make clear those analogies. So random variables in classical probability, it's a measurable function who is going from a space omega to complex number. And in free probability, it's an element of a von Neumann algebra that is a bounded operator on a Hilbert space. Expectations, you have the classical definition in probability theory. In a free probability is just the tracial state evaluated in A. And I will return on one of the prerequisites, one of the axioms in the definition of phi. At some point, we ask that phi of A star is positive, which has an equivalent property in probability theory. You ask that the expectation of positive random variable are positive. You will also analogies can expand to some special type of random variables. Positive random variables corresponds in the world of free probability to variables that can be written A times the agent of A. Real random variables corresponds in the world of free probabilities to auto-adjoint operator. And constant random variables correspond in the world of free probability to a multiple of the unity. So now we have already some analogies between a classical probability and free probability, and we want to go further in the analogies to have some more interesting tool which are maybe related, which I will okay, which I will make appear in applicated context, more precisely in the context of the study of spectrum of random matrices. So I will now give the free probability version of independent random variable. So it's a quite formal definition. So you have your non-commutative probability space, A phi, and you say that a family BI of subalgebras containing the unit is free if all family of indices A1 up to AN, which are alternating. That means that A1 is different from A2, A2 is different from A3, etc., etc. And all family of elements A1, AN, so that AK is an element of your subalgebra number K, BIK. If all your elements are centered, which means phi A1 is equal to 0, phi A1 is equal to 0, then the product of your element, A1 times A1, is also centers, which is the implication you can see on the screen. Just observe that I don't ask all the indices to be different. It's just A1, the index AK, which should be different from AK plus 1. A1 can be equal to A3 if we want. So now that we defined subalgebras that are free, we can define the sets that are free just by asking that the generated unital subalgebras are also free. So it's quite a formal definition, and we don't really see from where it's coming, but we can already do some nice computation which have analog in the classical probability theory world. So if we have an element of a non-commutative probability space, like A here, and you define the A prime as the element, but you subtract the expectation, that is phi A times the unit, and you not A bar the expectation. You can write A as the sum of A bar. Oh, there is a mistake. A is the sum of A bar and A prime. And phi of A prime is, of course, centered. And phi of A bar is equal to phi of A, just the property of linearity. So this will this small rewriting will allow us to do some computation. So if you take two elements B and C in your probability space, the phi of the product of B and C can be written this is the first equality, as phi of b prime plus b bar times c primes plus c bar. If you expand the multiplication, you have four terms that you can treat independently using the linearity of phi. So the first term, phi of b prime c prime, is equal to 0 just because b and c are independent elements. They belong to different free subalgebras and they are both centered. So phi of b prime c prime is equal to 0. For the second term, phi of b prime c bar is equal to phi of c bar times phi b prime, just because c prime is a scalar, c bar is a scalar. And phi of b prime is equal to 0. So the second term is also vanishing. The third term is also vanishing. So you are left with phi of b bar c bar, which is equal to phi of b bar phi of c bar, which equals phi of b phi of c. So at the end, you prove the equality phi of bc is equal to phi of b times phi of c. So if you remember, phi is supposed to be similar to the expectation in classical probability theory, and your element BC are supposed to be identified in classical probability theory as random variables. So you have phi of BC equal phi of B times phi of C, but this equality here is well known in classical probability theory as the expectation of two independent random variables is the product of the expectation. So for three elements, you have the same identity. Okay, you can do the same type of computations for more complex calculus. For example, if B1 and B2 are in an algebra B, and subalgebra B, and C1 and C2 are both in a subalgebra C. You can compute phi of in end, you suppose, of course, that B and C are independent. Then you can compute phi of B1, C1, B2, C2. You just do the same trick. You rewrite B1, C1, B2, and C2 by centering and decomposing those elements. Then you expand, and then you treat each term separately, and you find at the end formulas. You find at the end the formula which I have written here. Observe that in the final formula, like inside phi takes value on product of elements who are all in the same subalgebra. B1, B2, both are in the same algebra, etc., etc. In particular, if you want to compute phi of A plus B at the power n, you can use the same trick, and at the end you will find a polynomial in two variables evaluated in the moment of A and B. That is evaluated in phi of A at the power k for k from 0 to n. So the moment of the sum of two independent variable in non-commutative probability completely depends just on the moment of the two variables. That will be useful. So now we have an analog of independence in non-commutative probability, and we want to go a step further by having an analog of the law of random variables. So that is way more technical than in classical probability theory. Because you need functional analysis. So I will not go into the details, but I will try to give an idea of what happens. So you have a random variable in your non-commutative world that is an operator x here, and you consider a function from R to R, which is continuous and bounded. There are in functional analysis you can define just by using spectral measure, I will not go into the detail, an operator f of x, which is by the property of Neumann algebra. That is why we ask for closure, etc., etc. You can prove that f of x is still in your non-commutative probability space. So just observe that f of x is of course not the composition of f and x. X goes from h to h, and F goes from R to R. It's really a functional analytic definition. So you can prove, now that I said that, there exists a unique measure, mu in this X, such that for all bounded Borel function, the expectation of f of x, that is phi of f of x, is the integer over the real numbers of f along this function. This is analog for those who remember their probability lessons, to the transfer theorem said that the expectation of f of x, if x is a usual random variable, is the integer of f along the law of x. So you have an analog inequality, but the difference is in the definition of f of x. So this probability that is uniquely determined and well-defined now, we call it the law of x. So we have a way now to define the law of random variables in the non-commutative setting. Now that we know how to define the law, we can still go a step further, up to free convolution. So we want to define convolution in the non-commutative setting. So for those who remember their probability lesson, you know that to define convolution of two measures, you just take two random variables, and you say that the convolution of mu and lu is the law of the sum of these two random variables when these two random variables are independent, and x has law mu and y has law nu. This defines the convolution, and you can check that it doesn't depend on the particular realization of x and y. So in non-commutative probability theory, you do exactly the same. You take you consider two measures, mu and u. There is a result saying that you can realize this measure as law of random variables that are free, so independent in the sense of non-commutative probability space, and defined on the same probability space. So the sum of the two random variables is well defined, and you just define the free convolution that I note like that as the law of the sum of x and y. So this law, as in the classical setting, does not depend on the particular realization of x and y. It does not depend on the choice of x and y. So you have defined a free convolution in a non-commutative probability, which is already satisfying. And in the next slide, I summarize all the work we have done to generalize some concepts and of classical probability theory to free probability theory. So you have random variable, expectation, a certain type of random variables, independence, convolution. But we ask, why have we done all this work? How does this naturally arise in an applied context, for example? So I will present you a result where free convolution of measures naturally appears, which is in the context of study of the spectrum of the large random matrices. So to do that, I need some notation, a piece of notation. So if you have a matrix A, which is an Hermitian matrix with spectrum lambda 1, lambda n, so it's counted with multiplicity, so the size of the matrix is n times n. You can define a measure mu A, which is basically counting the spectral values, but is renormalized. So the knowledge of this measure, nu A, which is defined by this formula, this is a Dirac measure, is essentially equivalent to the knowledge of the spectrum of this Hermitian matrix A. So this notation will be useful for what happens after, because you can define it for matrices which have different dimension, but it's still object even for matrices of different dimension that live in the same world. So we can introduce convergence and so on. Okay, so this is for the definition of new A. You can also define UN, the set of unitary matrices of size n times n. And you defined OA, the set of Hermitian matrix that have the same spectrum than A, which has this form according to the spectral theorem. And you have a way, I will not dive into the details, to choose uniformly matrices on this set OA. And the measure that expresses this uniform choice, I will denote it by rho of A. So now here comes the theorem where free convolution appears. If you have two family of matrices, AN and BN. So AN is a matrix, an Hermitian matrix of size n, BN also. Okay, you have additional hypotheses. I think you have to ask that the norm is bounded and so on. And you consider a pair of probability measure, let's say with compact support, such that the new AN is converging to new 1 and new BN is converging to new 2, where I defined new A for any matrix as before. So it's a kind of convergence of spectrum, if you want. If A prime is a random variable valued in the space of matrices, and has low rho an as defined before, and B prime has low rho bn, then you can say you have the following convergence result. The measures new A prime plus B prime, so the spectrum, loosely speaking, the spectrum of A prime is B prime plus B prime is converging to the spectrum of the free convolution measure of new 1 and new 2. Okay, this is a very nice and surprising result that can be proved via free probability theory. And I said surprising because you know that if you take two matrices and you look at their spectrum, the spectrum does not just depend on the spectrum of A and B, but does depend on the particular structure of the matrices A and B. But here you see that when the size of the matrix are going to plus infinity, and the spectrum converge, the individual spectrum converge, the spectrum of the sum also converge to another measure, and so does just depend on the spectrum of AN and BN. Because we said already that the spectrum of nu 1 and nu 2 does just depend on the nu 1 and the nu 2. Okay, so this is a quite surprising result, at least for me, and I hope it motivated you to to appreciate the free probability construction. So
For the
now,
interruption, you have
yeah.
10 minutes left.
How much?
10 minutes.
10 minutes. Okay.
Thanks.
Thank you, Andrea. Okay, I will go a little bit quickly, so I will pass on historical details. Now I will speak about optimal transport. I will pass on historical details about optimal transport. But let's say the main objective in optimal transport is to transport mass from a place to another place. So if you have a mass configuration given by a measure mu and a mass configuration given by measure mu, you want to transport the mass given by mu to the mass given by mu. And we want to do it by minimizing the transport cost. You want to that the transport doesn't cost too much. You don't want to send mass from you don't want to send it too far. You want to send it, for example, if the transport cost is the distance, you want to send it really near. So, for example, to be less abstract and vague, imagine you have your measure mu is given by 2 points, which both have half of the unit, and your measure nu is given by 3 points, here in green. The first has 1/4 of the mass, the second the half, and the third 1/4 of the mass also. There are many ways to send the mass from the red points to the green points. So just for the purpose of presentation, I do 2 lines. For example, you have I present this on 2 lines, but you can imagine this is still on the same line. So, a way to transport the mass from the red points to the green points is that the first point is giving 1/4 of the mass to the first point and 1/4 of the mass to the third point, while the second red point is giving 1/2 of the mass to the second point. You have, of course, other ways to do it. You have an infinity of ways. For example, you have this transport. So the first point in red is giving half of its mass to the first point in green, and the first point in red is giving half of its mass to the second point in green, and the same occurs for the second point in red. Of course, you don't have always a measure with finite support. You can also have measures given by a density, and it's not always in one dimension, but it can also be measure in 3 dimension, which is the most natural case. For example, if you want to transport some sand from a place to another. So formally, how can we present this problem? So this problem just is called Monge-Kantorowicz problem, and can be presented as follows. So you have two measures, the marginals, mu and nu, and you have a cost function, let's say, that takes a positive value. So the admissible solution for the Monge-Kantorowicz problem are called transport plans. And we ask that the marginal constraints given by this equation are verified. So you ask that for all Borel sets defined on the space where mu is defined, the mass which is leaving from A, which is P of A times F, is equal to the mass given by mu on the set A. And similarly, for all Borel set B of F, you ask that the mass that is going to B is given by nu of B. So the Monge-Kantorowicz problem, in the Monge-Kantorowicz problem, you want to minimize amongst all the transport plans from mu to nu, the global transport cost, which is given by the integral of our cost along the transport P, that we will denote by G. There is another way to see this problem, in a more probabilistic interpretation. So you have the same data, so you measure mu and u and your cost function c, and you want to minimize the expectation of c of xy, where x is a random variable with low mu, and y is a random variable with low nu. So in general, it is very hard to compute the solution of this problem because it's an infinite dimensional problem in general. When you have it's very general measure, but in some cases it is possible. For example, when you are on the real line and your cost function is convex transformation of the distance. For example, you can imagine the square distance. Then you know the solution explicitly of your optimal transport problem, and it is given by this particular transport plan, which is by a particular transport plan, which is called the monotone transport plan. So I will not go into the details. I don't have much time, but basically the monotone transport plan is you send mass from the left to the right, because you have a direction, you are on the real line, and you send it the more possible you can on the left. So if we go back here on our pictures, it is this plan because 1/2 is sending as much as possible on the left, 1/4, then as much possible to the left. That is 1/4 to the most left point, this, which is the second point, and then same with the second point. Okay, it was a kind of quick, but I hope you had you understood the idea. So now, okay, maybe I will go a little bit I will not do this slide, but in some cases, you can say some stuff about the form of the solution of your optimal transportation problem. In particular, when your measure is nice enough, it means it is absolutely concluous toward the Lebesgue measure. Your transport plan is given by transport map. And you, in some cases, like with normal laws, you can explicitly compute the solution and so on. Okay, I have to be a little bit more quick because I want to speak about Wasserstein distances. So this is okay. I will not talk about that. So now for Wasserstein distances, we are not interested anymore in the form of the solution of our optimization problem, but just we are just interested on the value of the problem. So you can define P of X as the set of probability measure that has a P moment that is finite. And you define the Wasserstein distance from U to nu as the transport cost from U to nu for when the cost is the distance at the power P. And you do some normalization by putting everything at the power 1 over P. Uh, so this Wasserstein distance is really a distance. It gives a way to measure how far mu is from u. So it defines the distance on the space of probability measure that have a finite p moment. Okay, this is you have to verify that it's not trivial at all, especially the triangular inequality. Okay. So now we have a distance on probability space, and we want to look a little bit at the topology induced by this distance. So we know a classical topology when we work on probability spaces, that is the weak convergence topology. Which is defined as follow. If you have a family of a sequence of measure mu n, you say that the sequence of measure mu n converges to a measure mu if for all continuous bounded function x, the integral of x along mu n is converging when n is going to plus infinity to the integral of x along mu. So what is the relation between the Wasserstein metric, that is the topology associated to the Wasserstein distance, and the weak topology? So the relation is given by this theorem. Mu n is converging to mu for the Wasserstein distance, if and only if mu n is weakly converging to mu, and the p moment of mu n are converging when n is going to plus infinity to the p moment of mu. This moment condition is quite important because you can find counterexamples when you have weak convergence but not convergence of the moment. I will not insist on that, but for example, if the space X is compact, it's completely equivalent to weak convergence. So convergence in Wasserstein space and convergence to weak convergence is almost equivalent, at least from a topological point of view. So I give some reason why Wasserstein distances are nice. You have a lot of reasons, mostly geometrical and for computational reasons. And it's more natural in mathematical settings where optimal transport is naturally involved. How much time do I have on this?
Um,
Yeah.
0 minutes.
0 minutes, okay.
Yeah.
So I will stop here. I will just say,
If you want to say something else,
yeah, I will just say two sentences,
yeah.
two additional sentences. Okay, you
I,
have.
I'm giving the seminar, and it's fine with me if you continue a little while because I think you
Oh,
had a
okay.
good preparation. But maybe it does seem overambitious to do this in 30 minutes.
Okay. Yeah. I will do just two. I will just say 2 words about duality,
Okay.
the dual
Thanks.
problem, really quick, less than 5 minutes, I promise you. So you have the primal problem, which is the Monge-Kantorovich problem, and to this primal problem, you can associate a dual problem, like often in convex analysis. Uh, So this is the following problem. You consider pairs of function and you have a constraint. The constraint is given by this line. You ask that for all couples xy, p of x minus p of y is inferior or equal to c of xy. And then among all these admissible pairs of function phi psi, you want to maximize the value of these integrals. So there is one obvious inequality, which is given here in this block. It is the supremum is inferior to the infimum for the primal problem. So the obvious question is, do we have equality? And the answer is surprisingly yes. You have equality, and this is coming from a min-max theorem that you have to prove rigorously, and it's hard work to prove that. Okay, that's it. Okay. Under some regularity condition, you can also assume that you have a solution to your dual problem, and you have what is called complementary slackness, which is a way from from the primal to the dual and vice versa. So I think that's it, Andrea. We'll stop here. Thank you everybody for your attention. I hope this was not too fast because.
Thank you. Thank you very much for this very nice pre-seminar. Are there any questions or comments? Also, if you are online and you have some question, please unmute yourself. Just a quick curiosity, since you had to prepare this pre-seminar, what do you think are the most tricky parts of doing the non-commutative setting?
Oh yeah. I think the most tricky part, at least when I discovered like this field, is to understand like all the equivalence definition of von Neumann algebra and to really be not afraid and understand like the functional analysis background for all the definitions. You know, for example, when I defined f of x, you have to use a very powerful result of functional analysis like a spectral theorem, and, which is kind of tricky when you don't do it every day.
Okay, I see. I can imagine. Are there other questions or comments? If not, we can thank Armand for the nice seminar. Now we do 5 minutes break and then there is the seminar.